Yeah, so you've seen the data. This is actually the way it was presented when they were trying to figure out whether or not these O-ring failures were caused by what was causing them. So each of these numbers, so you can see that there are 24 launches here. Each number is associated with 2 boosters. These are the boosters on the side of the the big tank that the shuttle flew on. And the O-rings are at these joints and these boosters, they're representing kind of the funny part is representing not only which O-rings failed, but how badly they failed. Temperature is represented as the number on the rocket, you can see kind of which O-rings failed on which booster at which temperature. And looking at this, it's not at all clear. Looking at this plot, it's not at all clear that it's temperature that's causing this problem, right? In hindsight, we know that it's temperature, and we know that we've never flown anything. In fact, the temperature flight was actually not the one difference in this case. Was the current temperature, I think, is 43 degrees. The temperature flight was much lower. The Challenger flight was much lower than that, like in the high 20s, I think. And so it was even, much colder relative to the average flight. And it's not, this plot wasn't shown. I mean, they didn't make this plot to confuse people, right? The plots you saw in this case were maybe a little bit intentionally misleading for the purposes of a case discussion. But there's a good faith effort to try to figure out what's going on with this issue for the O-rings and the boosters. And we'd seen failures. We'd seen them up to and if you look at this data and if you plot it out, it's the exact same data you got from this document cam right here, right? There's no difference. Let's see here. There we are.
Yeah.
Those numbers are the same. Huh?
Looking at that representation now makes me think that looking at the data in a different way, which we did, in previous classes, makes sense to see the temperature difference. But I also wonder if this helps you visualize the fact that part of that solid booster was facing the sun. So you can have difference in temperatures from one side of the booster to the other versus, because of the solar radiation. So I wonder if there was a way for them to determine if the failures were on the side away from the sun where it's going to be colder. It's going to be air temperature versus a little bit of heating from the sun.
So certainly that might have been one of the things they were looking at, right? Maybe there was certain stresses associated with the asymmetry of the rocket design or something, right? They were not. There's a lot of things they're trying to get at in this plot, but they missed the one giant thing, right? I mean, because whether or not you are facing the sun, if you're now, again, all these temperatures are 53 and above. We're now all the way down here in the high 20s. If you're facing the sun, it's not going to make much difference when you're talking about a 30-degree difference, right?
It can be quite a bit of difference. I know I deal with it on a telescope, and we'll get 20 degrees C heating from the sun on the big side of our enclosure that's facing the sun versus the side that's shaded.
Sure. So that's certainly fair. But my point is that if you're still seeing failures when it's at 53 degrees and you drop at 30 degrees, anything that's happening there is only going to be amplified, right? Yes. Dennis.
So the way the case was presented, it's a decision point before the race, right?
Yep.
So one thing I don't think I've ever actually understood, did they really do some sort of decision process and look at data before the flight? And is this what they looked at?
This is what they looked at right here. This is, they looked at other things, right? And there's an important caveat here. The information on this page is prepared to support an oral presentation and cannot be considered complete without the oral discussion. Let's not judge them too harshly because a lot of things were going on. But this was before the Challenger disaster.
Yeah, okay. And they did talk about the fact that they have double O-rings at each one, and so what are the chances that both O-rings would fail at any of the segments?
Yeah, this is, they looked at this. It wasn't that they knew that they were convinced it was unrelated to temperature, but they flew anyway, right? why did Challenger flop?
Pressure. Pressure to.
Yeah, did they want to beat the Soviet Union?
If they didn't win, I mean, yeah.
If they did
They
win, the
didn't
Soviets
find
would win.
Yeah, weren't they like delayed it multiple times at
Yeah.
that point already? There was some
They're getting
pressure to.
That
align with
teacher on
that.
board, part of the crew,
Yeah,
a lot of PR.
it was PR. They were already delayed. There was pressure. There was there was go fever a little bit. I think if you want to look at a kind of post-mortem analysis, I think people do point to the go fever. There was like big payoffs, right? The big payoffs, and if you look at the data in a certain way, yeah, there's a risk. I mean, it's not like we didn't know that there wasn't a risk, but like everything's a risk, especially something like spaceflight, right? The problem was not identifying a risk. It was not assigning the probability that it deserved.
Or the cost, really. I mean, if we're using the numbers we use, I'd say the cost would be much higher than the.
So you're saying like here, I mean, what we've got here is a delta of like 2.7 million, but you would say that instead of, it would be a much larger gap, much more negative number.
Right.
Yeah, I mean, this is in this case, what we never acknowledged was that engine failure might be dangerous for the driver, right? That wasn't represented as part of the case, and nobody brought it up in the discussion. But like, the engine failure might be embarrassing to a NASCAR team, or it might get the driver killed. So it's not that wasn't a possibility even in the presentation we had in the case. It just wasn't one that was explicitly acknowledged. Now, why is this case in a data mining class, right? There's very little data here. I mean, this is kind of the opposite of what you think of when you think of big data, right? This is 24 launches. It's enough to do a logistic regression. It's not enough to do much else, right? The point is that it really matters what questions you ask of the data. It really matters how you visualize it. It changes things dramatically, whether or not you kind of look at it in its full complexity, trying to look at all things at one time, or you try to isolate out, individual factors here. In this case, I think it's probably pretty obvious. And I bet, Ryan, unfortunately, you ruined the final vote, where most people would have switched to don't race after seeing this plot. Because the second you realize it's Challenger, I think people start to realize you probably shouldn't race. But I think even if we had that vote, I think most people, once they've seen this, would have probably decided not to race, even though there was a bunch of money on the line. Precisely for Caroline's point, that we've now changed the probabilities of this bad event, even if they're not actually bad enough, given what we kind of think now, it still would have dropped things to the point where it would have been better for us not to race. So as we go through this class, we're going to spend a lot of time on thinking about how to represent the data well, to prepare us well for making decisions from it. And we're going to see some bad visualizations. That's part of it. But hopefully we'll be able to combine those bad visualizations with proper testing down the line, such that we can weed out when we come up with bad visualizations and get back to the core of the relationship. All right, any final thoughts before we take a break? All right. Yes, Allie.
So if this is going to skew this percentage, how is it going to skew the overall 37.5%? Just visually here.
So so these numbers here add up to 100.